Good morning, Rob. As all the participants are joining, I see a few of them already joined in. Typically, for 5 to 7 minutes, what we would like to kind of understand is your life journey. Essentially, from high school would be good, is where exactly you did your high school and how you ended up in microelectronics.
Okay, Baljeet. First of all, thank you for letting me participate in your webinar series. I greatly appreciate it. And I hope that the participants enjoy it. I'm going to go back further than high school. And I'm going to say that my father was a photographer in the Navy. And he was aboard an aircraft carrier and took all kinds of pictures of planes landing and movies of fleet maneuvers. And when he got out, he wanted to continue a career in photography. And everybody said that if you want to do anything in photography, you should go to Rochester Institute of Technology in Rochester, New York, where Eastman Kodak is. And so my dad came to RIT late 1950s and started studying not just photography, but photographic science and instrumentation. So he was kind of a photographic engineer, if you will. And so that's my dad. And I grew up around RIT because after he graduated, he got a job working at RIT. And so he was doing printing and color science and photography all rolled together. And so I grew up in the town of Henrietta, right where RIT is located. And I got exposed to a lot of the different programs. I didn't follow exactly in my dad's footsteps, but I chose electrical engineering. And then part of the great thing about RIT is they have a required cooperative education component to a bachelor's degree. So you have to do 1 year of practical paid employment. And I was lucky enough to get a job in the semiconductor industry at a company called Fairchild, which was one of the very first semiconductor companies. And that was in the state of Maine. And lo and behold, what I was doing was chemistry and photography and physics, everything but electrical engineering. But I was making logic gates. I was making quad 3-input NOR gates and TTL, transistor logic gates and so on, and working on actually sort of the advanced packaging of its day back in the late 70s, early 80s. And that led to another job in Silicon Valley, again with Fairchild, working on failure testing for electromigration of some of the early aluminum chip wiring. And then I graduated and went to work for Fairchild again on a packaging area, and then got offered a job to come teach at RIT because I had made the first transistors at RIT. And I knew how to do it and run all the equipment in the lab. And so you'll see that the focus of my talk today is very much on the basics and getting started. So if you're tuning in for super advanced FinFET stuff, that might not be what you're going to get.
No, it's exciting. Could you talk a little bit about your experience at Fairchild, being the initial company in US in semiconductor? What were you working as? Was it process engineer, design, or what exactly?
Initially I was a process engineer in a line that was doing what's called tape automated bonding. And so they were doing a photolithographic process for patterning copper interconnects that could easily be thermal compression bonded to gold bumps grown on the chips. And you could do all the bonds at one time instead of individual wire bonds. And so that involved mechanical drawing of tools. It involved researching the chemistry and the yield and so on. So I learned a lot about manufacturing and how it encompasses pretty much everything you do. So that was really kind of process, but not in the sense of ion implantation and chip manufacturing. I have delved deeply into that much later in my career, but that's how I got started at Fairchild. And the other thing at Fairchild was very interesting because some of the very early pioneers of the semiconductor industry were working there. Early effect in bipolar transistors was there in Silicon Valley. Bruce Deal of the Deal and Grove oxidation model was my second level supervisor there, so I got to eat lunch with him. So it was very exciting for me to meet all these famous people as a young engineer.
Excellent. Rob, one final question before we jump into the session. You have been both sides into working in a fab and then into academia. For our listeners, what is a typical mindset or personality that one has to develop when they go into academia? Because a lot of faculty members kind of are listening to this. They would love to hear the mindset that's required to be a faculty in semiconductor.
Well, I can kind of divide my answer into two parts. One part is that at universities, we've been trained by funding agencies to follow the research dollars and come up with innovations that are going to save the day and so on. But really, it's research whatever can get you funding, because that's what the university is interested in. Semiconductor manufacturing is so complicated, involves such expensive equipment that it's very difficult to do research in that area and get funding in that area. So, but that's actually where the jobs are located. So it's very hard for a faculty member to say, I'm going to concentrate on teaching somebody the skills that they need to get a job, because they're not bringing in funding for that particular reason. But with the US and the CHIPS Act, one of the things that is a focus is, what if we have this great research that we think could potentially down the road impact the semiconductor industry? How do we bring that into the semiconductor manufacturing? So they call that the valley of death. You have a great idea, you want to get it manufactured, but you can't figure out how to get across the valley of death. And I think that people are now realizing that building the skills and teaching the skills at a university of how do you get across that valley in sort of a guided tour mode will help promote better success of future researchers in getting their wonderful ideas implemented. So that's sort of my answer to that.
Excellent. Thanks, Rob. Let's kick into the session.
I'll be in the chat room too, so people can hit me with questions there.
Yeah, sure. So I wanted to kind of invite everybody who's joining right now. It's a wonderful initiative by Ajuba. We have started a fortnightly webinar series on skill development. This is our fourth webinar, which is going to be on semiconductor processes from bare wafer to test. Just so that people are aware, this is all free of cost and effort to kind of train people in the new high-tech semiconductor and cybersecurity world that is needed out there. All our past webinars are on our website. We started off on May 21st on cybersecurity. Thrive DX team came online and they gave their talk on May 21st, followed by June 4th, which was on semiconductor. This was from Amos Dror from Applied Materials. He's the CTO of Applied Materials and AGS Automation Productions Group. The third webinar was on June 15th. In fact, from RIT itself, and Dr. Nishi Rastogi talked about artificial intelligence and its role in cybersecurity. All these webinars are available on our website. You can go and view them at any time. Today's webinar is going to be on semiconductor. So as you can probably see that we kind of switch between semiconductor and cybersecurity. What we're going to cover today is the introduction to semiconductor processes, wafer preparation, semiconductor fabrication techniques, backend processes, testing and quality control. Then we'll talk about Ajuba's initiatives in India, followed by Q&A session. And finally, we'll talk about our next webinar. Before we dive into the session, I would like to introduce our today's speaker, Dr. Rob Pearson. As we have already seen, a man with a passion for teaching the entire spectrum of microelectronics. From device, circuit, process design to manufacturing, testing, and reliability. In fact, I can tell all the listeners, I had the first-hand experience of being a student for Dr. Pearson at Rochester Institute of Technology. I was privileged to graduate under his umbrella. So today I'm working again with RIT in different fronts. It's really brings a lot of happiness to me. He started, like he mentioned, his career at RIT in 1979. He started with his degree in electrical engineering, but started building silicon transistors because RIT had this amazing co-op experience. Later on, after graduating in 1982, he became the first faculty that was hired by RIT in microelectronics program. A man who has been part of developing the entire microelectronics program along with Dr. Lynn Fuller, who was the department head at that time. He has not only kind of been developing the curriculum under ABAT, but also has been very instrumental as a consultant in with various companies in US, Mexico, Singapore, and China, and has served as a committee member with different organizations. So let's kind of dive into the talk from Dr. Rob Pearson. And let's hear what he has to say about microelectronics.
Hello, my name is Rob Pearson, and I am a faculty member in the Electrical and Microelectronic Engineering Department in the Kate Gleason College of Engineering at Rochester Institute of Technology, Rochester, New York, USA. I'm going to be talking to you today about semiconductors. We're going to go from bare wafer to test. I'm going to keep this at a very low level. So if you're expecting to learn all the secrets of FinFET manufacturing, this is not the talk for you. Let me give you an idea of what I have as a target audience and what I want you to do. My objective is to explain basic semiconductor electronics to you at such a level that you could easily understand it, and in turn explain to a high school student to get them excited about this field. Why? Literally, the future of mankind will be determined by how we design, make, and use electronic and photonic devices. I don't make this statement lightly. I truly believe this. I think that the transistor has put us at an inflection point similar to the invention of movable press and the printing press and the Gutenberg Bible. The transistor is the most important invention in history. Look at how the world has changed in the last 75 years since the invention of the solid-state semiconductor transistor. The semiconductor industry is nearly a $1 trillion a year industry. It's just behind oil, automotive, and healthcare industries. And it makes up a substantial component of these other industries. But it's not just about the money. Semiconductors are a big part of those industries. But if you think about robots at farms and in the operating room and telemedicine, entertainment, communications, the list goes on, and it all involves semiconductors. So I want to emphasize critical thinking in 3 areas. One area is devices, And that enables circuits and systems, and it's really the key to everything. But to make those devices, we have to choose materials and unlock new capabilities, but it comes at a cost, not just the material cost, but the processing cost. So the third area is the process. How do you make or manufacture better devices and incorporate these new materials? And in this diagram, we see devices at the cross point or intersection point of semiconductor materials, processes, and circuits. Materials and processes involve physics and chemistry and manufacturing, and the materials influence the devices which are built into the circuits, which become electrical engineering, and then go to the system level, which is computer engineering, and then we can take it to the software level, software engineering and artificial intelligence and so on. But it has its roots in the devices and the improvements in the devices. So we want to put electrons and photons to work. Doing what? Sensing things, lighting, communicating, storing information, calculating things, collecting power, delivering power for electric vehicles, for example, or for your home, displaying information, and so much more. Like I said, transistors are into basically everything we do. Let's look at some electron pros and cons and photon pros and cons. Electron technology is well developed for signal processing. Think of your microprocessor, signal amplification. We can have very densely integrated circuits that's enabled a lot of what we're talking about. Memory is integrated into this. Now they're talking about computing in memory. The bandwidth is a little bit smaller in terms of processing speed. The power consumption can be higher. Photons, on the other hand, are very fast and have a very high bandwidth and offer very low power data transmission and so forth. It's currently difficult to do signal processing strictly with photons. It's not as densely integrated with waveguides and so on. There's really no good solution in terms of signal amplification. And the memory function is also a little bit is also not as well developed. So these two are currently linked. You do some things with electrons and some things with photons, and you cross back and forth between these domains. And how you implement these are important to the success of the system that you're trying to create. So controlling the effect of the electrons and photons. If you were controlling the flow of livestock, you would need gates and fences. Gates are open or closed. The pasture is inside the fence and the livestock moves there. Crops are on the outside of the fence and the livestock is prevented from going there. So I'll say the area where the pasture is inside the fence would be a conducting wire, but outside of the fence would be an insulator. So for digital electronics, you need wires and switches are either opened and closed like the gates. The wires allow the electron or photon flow if it's a waveguide, and then insulators or dielectrics block the flow of electrons. So continuing with our wires, insulators, and switches, you're familiar with house wiring done by copper. Typically, the insulator is the plastic jacketing around the wire, the paper stuffing in between, and the outer plastic jacket. Here's an example of a mechanical switch, all right? And then this is either on or off, but we could also have an analog function like a dimmer where we get at various levels of illumination besides just on and off. So continuing with the idea of digital versus analog signals, I could have a perfect digital switch where I can go from off to on with some sort of switching control. With our light switch, it's mechanically flipping the switch. In a real digital transistorized switch, I electronically can switch from the off to the on state. And this could be either switching currents or voltages. Now for analog signals, we have a signal that continuously changes with time. It's not off or on. It's in various levels in between. And frequently we need to take a weak analog signal and amplify it and make it much stronger. So I mentioned the idea of a transistor acting as a replacement for that mechanical switch going from an off state to an on or conducting state. And so this is an example of what we call a positive channel enhancement mode electric field effect transistor. All right, it's got characteristics that look like this, but we can turn it off and we can turn it on. The details of the device physics behind how it operates is left to another lecture. In fact, just about every single slide here could be a full 40-minute lecture in and of itself. Once we have transistors, we can put them together. It turns out that two transistors can be used to create what's called a logic gate called an inverter. An inverter takes a low signal or a 0 and outputs a 1, or it takes a high signal, a 1, and outputs a 0. So an ideal inverter would have a characteristic that looked like this red line here. Using the PMOS transistor from the previous page, I can construct an inverter that has this black characteristic. Well, not ideal. It can do the job and is easily fabricated and forms the basis of understanding how even an ideal versus non-ideal would work. It turns out that a much more sophisticated complementary CMOS inverter is nearly ideal. Having trouble with my mouse here. So let's design these electrical switches, and we want them to work faster. We want them to be smaller so we can connect more of them together to increase our functionality. We want it to use less power. We want it to cost less and also be more reliable. Pretty ambitious list. We're going to employ critical thinking, all right, and say, what devices do we choose? What are they made out of? Materials. What processes are required to use those materials to make those devices? What can we do and what can't we do in order to address these? So three things that we need, as we've already mentioned. We need conductors, metal, like aluminum, or maybe doped silicon. Doping simply means that we're adding impurities to the silicon to alter its electrical conductivity. And this would be used for wiring together components. I'll talk a little bit in a minute why we're using aluminum as opposed to copper, which was in my example previously. We need insulators. Silicon dioxide or glass is a very good insulator. And so this allows us to have wires with different information do not inadvertently touch or short circuit to other wires, conductors and insulators. But they're not part of the control, they're passive devices. We use semiconductors, all right, to create regions that control the electrical charge. So we can have positive doped carriers in our silicon or negative charge carriers in our silicon. And so we call these semiconductor regions active materials for making things like resistors, diodes, and transistors from which our silicon, which our circuits are made from. So we'll have the acronym MOS, which is a metal oxide semiconductor stack, which uses all of these components to make our transistor. And it turns out silicon can provide all three of the things that we need. I can take silicon, which is group 4 of the periodic table, and if I add group 3 elements, I end up with positive charge carriers. Similarly, if I take silicon group 4 again, and I add group 5 elements, I end up with an abundance of negative charge carriers. And so it's these doped silicons that make the semiconductor region. On the other hand, if I take silicon and I oxidize it, I get silicon dioxide, which is a glass, which is a great insulator. So here I have conducting silicon, insulating silicon, positive and negative type which allows me to do the control functions that I need. So silicon is very versatile, and it's why it is the most widely used semiconductor material in the world at the moment. I mentioned not using copper. Statue of Liberty is made out of copper, and as we know, it's just kind of got this green color, which is a copper oxide. And so this is a processing problem that took years to overcome, and the semiconductor industry started with aluminum, and that's what we're going to use in our example. But copper is a better conductor. So a little more about the electric field effect that we use to make a switch. An electric field is an electrical line of force that is a result of putting a applied potential or voltage across some distance. So in this particular example, I might have negative type silicon with a glass oxide layer and then a metal electrode. If I have the electrode at -5 volts, I'm going to attract positive charge carriers here due to the electric field. So I have a very high, strong electric field here. I can talk about magnetic fields as an analogy here. If I take a magnet and an insulator and have some iron filings, I can attract these iron filings to the bottom of the insulator. And if I were to move the magnet along, the filings would move along as well. And that's how we're going to actually envision current flow. Now, if I were to take this dielectric or oxide glass material and make it very thick, with the same voltage applied, the electric field is too weak to invert the surface, and I don't get the type of on behavior. So this is off, this is on, but this I couldn't turn on. So I need a way to turn this on and off. If I made this 0 volts, this would be off, -5 volts, on. This one, 0 volts, it's off, -5 volts, it is still off. So this acts as an insulator between these types of devices. Now, we're going to look at 3 key wafer fabrication operations and how we make an integrated circuit. And so we'll talk about layer operations, adding or removing layers, oxide, aluminum, etching or removal. We're going to look at ion implantation as a way of adding things. We can also talk about oxides and aluminum deposition. Just removing and adding layers in a blanket form everywhere is not what we need. We need to also introduce the concept of creating a pattern before or after an operation so that we have materials exactly where we want them and only where we want them. Here we're going to be using 4 different layer patterns, and we're going to be using a technique called photolithography. And as I already mentioned, doping is a method of changing the electrical properties of certain regions by adding a little bit of something to enhance the performance. So in our case, we're going to add a little bit of boron into the silicon to create positive charge carriers that enable our transistors to work. So here's an example of deposition. Think of snowfall, a blanket of snow everywhere. We're in New York. This was my back deck, 16 inches of new fallen snow. Once it's deposited, we have to think about removal. This is an example of patterning the snow by shoveling a pathway, all right? This is a serial operation, 1 shovel full at a time, and it would take us a very long time to do a complex pattern of snow removal. Can we think of a parallel snow removal operation? I could think of one. What if I had sidewalks that had heaters in them? As the snow fell, it would melt on the sidewalk and it would all happen at the same time and it would not be a slow operation. So parallel operations are definitely what we're looking for in terms of speed of processing. So getting back to the idea of patterning and layering together, here's an example of what we call a stencil. I went outside to the parking lot and there was a plywood stencil on the ground. They came and they did an additive process of applying paint, and then they removed the stencil. Notice the the stencil was actually covering up the blue square, which I didn't know was there. But now we have that patterned white paint here. So this is an additive process for the white layer. And it had to be aligned to the blue square. That's also another thing. So not only do you have to have the correct pattern, but you have to have it correctly aligned. So let's start our simple 4-level transistor fabrication process. We're going to start with a bare silicon wafer. This is 150 millimeters or 6 inches in diameter, and it's about 0.7 millimeters thick. And it turns out that 99.9% of the thickness of the wafer is actually not used and is just there for mechanical strength during processing. So we're going to say that this is a negative or N-type wafer, pure silicon with a tiny bit of phosphorus added to make it N-type and electron conducting. Later, we'll be adding, like I said, boron to make some positive type regions within this same wafer. So we're going to do a wafer cleaning operation in batches of, say, 25 wafers at a time in heated chemical baths to remove any surface contamination. If you're making 1 billion 10 nanometer sized transistors per square centimeter, and you have 150 nanometer particle per square centimeter, it can ruin multiple transistors and cause your whole chip not to work. So wafer cleaning is an extremely important aspect, and contamination reduction is a really important aspect to control defects and increase the yield of working devices. So now that our wafer is clean, we're going to put it into a furnace and grow what we call the masking layer of the silicon dioxide or glass. So silicon is going to react with 2 H2O molecules to provide SiO2, the glass, and give off excess hydrogen. So this is an example of a furnace that is up at maybe 1100 degrees centigrade, glowing orange hot. It gets ramped down to 800 degrees and the wafers are being pulled out of the furnace. And you can see that there's now color on the wafers, which is a result of thermally growing this SiO2 layer. Now we think of glass as clear, but for very thin layers, we have constructive and destructive interference, much like the thin film of water that you see on or oil that you see on top of a puddle in a parking lot after a rainstorm. So the color is going to be dependent on these very thin oxide layers. So why is this called a masking layer? Well, think of what masking tape does, and we'll come back to that a little bit later on. So I want to introduce some Six Sigma concepts here, which means that we have a goal or a target for our oxide thickness and what that average value is. And we have a normal distribution that we could go 3 standard deviations or 6 standard deviations away, and we get performance of our devices at a lower statistical limit and an upper statistical limit. Anything beyond that is considered to be a non-working device. And for Six Sigma, it turns out that only like a couple dozen in a million devices are outside of this range for a good process. But that's a perfect world. What if the average result of our process involves a mean that is shifted over here? That means that there's some part of our distribution that's outside of this limit that is considered bad devices. And this is going to cost us money in terms of yield of devices. So we have to do our best to get the average back where it belongs. Another problem that can occur is, what if our average is right on target, but our standard deviation is spread out too wide? Now we're getting more bad devices here. We've got to tighten up our distribution and our quality control to get back where we want to go. So every single step that we do involves this kind of statistical process analysis. And here's an example over time of an oxide growth that's targeting 5,000 angstroms. And you can see that it's kind of all over the board, but maybe we're making some changes and improvements and we've tightened it up and we're on our average and our deviation is much lower than it was months ago. So types of variation that we're talking about are variation within one chip, which could cause problems, variation across the whole 6-inch wafer, from one wafer in a batch to another, from one batch from one day to another day, from one tool of the same type to another tool. Chasing down and reducing variation is the process engineer's daily challenge. So now that we have that oxide, all right, what do we want to do to it? We want to either make a hole in the oxide, like the picture over here, or maybe we want to leave a ridge of the oxide or a line or a mesa. And a slot is really just a long, skinny hole. So what defines the size and shape of the feature? It's the patterning. So remember our stencil. The shape of our stencil is what determines the pattern that we're going to end up with in our oxide. So this is an example of a subtractive stencil. Here's a person applying some layer, all right, of protective material, plastic-like, and now he's cutting out the letters individually by hand. So this again is a serial, slow process. And now he's sandblasting this with the masking material protecting certain regions and the openings getting the removal of the underlying stone. So this is a subtractive layer removal process. And back in the 1970s, when we were making circuits, we would have a design laid out on a large piece of graph paper, and we would take this reddish material over top of it, and it's hard to see here, but you can see lines through this underneath, and with a razor blade, he's cutting away areas and peeling this off. So this is the exact kind of same idea as the previous example. But this is a slow serial technology. We do this layout of all these boxes and patterns on a computer now and send it directly to some sort of a mask making apparatus. So serial production of an image, like cutting it or doing it with a brush stroke, is a very slow idea. So here's an image. Now, why did I pick a zebra as an image? It's because it's binary. Black and white, 0, no feature, 1, the feature. So here's a feature, 1, here's no feature, 0. This is a slow process. How can we do better than this? Well, if you go back to old-fashioned photography, this is a parallel image capture. You open the shutter, you get the whole image at once very quickly. So it's fast. So here's my object, a zebra. I open the shutter. Over here, the lens inverts the image and reduces it and captures it on the film. So there's a photochemical reaction. We then take the film into a darkroom and we develop it and we get an image. This is a grayscale image. We actually want only black and white of our zebra. I need to go and get the zebra negative image here. All right. Haven't taken the time to play with these images yet. But the entire image is captured in parallel. It's much faster. Designed with 1 billion transistors on it, requires terabytes of pattern information or pixels, data transfer rates in just a second or two of photo exposure. So that's extremely fast and efficient. So this is an example of my photo mask that I've created that is binary with ones or zeros with a feature here, and then that's dark or opaque and a clear field region around the features. This photo mask is 5 times larger than the final chip size, and we will use lenses to optically reduce this down to be much smaller. So all these features will get even smaller than they are there. So what do we want to make first? We want to create highly conductive semiconductor regions for resistors maybe, or for the what we call the source and drain parts of our transistors. And these regions will be implanted with ions, like I said, of boron, or possibly chemically diffused, which is an older process. The non-ion implanted areas will be masked off or protected from being implanted. So remember that masking oxide we grew? That's where this name comes from. And we want to control the shape of these regions, so that's part of our layout design. So the implant layer is going to be done in green, and that will end up being what we call a dark field mask, which you'll see in a minute. Now, there's 4 individual masking levels that are used individually, and each level has 2 possible results, that binary. We're going to use green to denote the implant level. Green 1 will be used to indicate the presence of an implant by making a hole in the oxide, and green 0 will be used to indicate the absence of an implant where it's masked by the oxide. So for the first level, there's only 2 possibilities: implanted, not implanted. Implanted, this is a side view, not implanted. Now, for 4 masks, each having 2 options, 2 to the 4th is 16 possible combinations of our masks. Keep that in mind. We'll come back to that at the end of the presentation. So here's a magnified view of the photomask layout for image transfer. And this is showing only the first level. I make 2 boxes. One is going to be the source of my positive charge carriers, and one is going to be the drain, and they're going to be separated by some distance. The length, 20 microns, is the separation, and the width here is 80 microns. Again, this is 5 times, we make a photomask with this, which is 5 times larger than the final feature. So this is a future hole for the source and a future hole for the drain, and this is chrome, which blocks the light. So what we do is we're going to coat the wafers with a material that is photosensitive and then expose them to ultraviolet light through that photomask, and the pattern will be transferred onto the wafer. And we're going to make many, many copies of that same chip design on a single wafer, and then we're going to develop this chemically and inspect it to see how we did. So here we go. Here's our design. Here's the photomask. We expose it and reduce it, and we get this tiny feature on our wafer. The green area is a plastic resist coating, and the purplish area is the opening down to the glass or the oxide level where we're going to be doing the etching. So this pattern transfer is called photolithography. And this is an example of not just one transistor, but many transistors connected that will be connected together into a much more complicated circuit, giving us the idea of how we could go to more and more complicated designs. The next step is to etch these windows. So they've gone from being purple to being the bare silicon color. And we then have removed the plastic masking coating to reveal that pink colored oxide. So now we have holes for ion implantation. And this is on that same oscillator circuit. This was done in a wet acid bath, hydrofluoric acid. And hydrofluoric acid is an isotropic etch, which means it etches downward as fast as it etches laterally. So there'll be some degree of undercut. But these oxide layers are so thin that historically the amount of undercut was not a big impact. Nowadays we use gaseous etching that is very directional and eliminates the undercut and allows even smaller features to be fabricated. Again, every one of these slides is a whole lecture in and about itself. So now we're ready to do the implant of the source and drain electrodes. we take boron ions and we accelerate them to a velocity of about 600 miles per second, and we blast them into the silicon in the openings, and we keep the photoresist and the oxide masking material on the wafer, and it's blocked or masked here. So boron ends up donating a positive charge, so that's why it's called p-type. And the actual beam is much smaller than this. It is scanned back and forth, and this is just a picture of RIT's ion implanter console here. Very unique capability that we have. All right, so step one, we've now created these specialized conducting regions that are going to make up our transistor. Now the pattern that we're going to do next is to create these thin oxide areas. And remember, the very thin dielectric or insulator what allows the electric field effect or transistor switching. But we also need excellent alignment to pre-existing features. So this is what good alignment looks like in red, and this is what good alignment looks like when it's all done through the microscope. And I couldn't resist putting this in as a joke. The T is obviously not aligned properly here. And so you can also see some of the combinations of the first two masking levels. Here's 1, 2, 3, 4, 5 of the possible combinations here. No, all 4 of the combinations are actually shown on this particular one. Now, if the alignment is way off, it's going to affect the operation of our device, and we would have to kind of remove the photoresist and try again. And this is after we've etched the silicon down to the bare oxide, because this is where we're going to grow the very thin oxide for our transistor. The inset picture here is showing something called an alignment vernier, and this is checking to see whether or not we're off in the Y direction. And it turns out that we've got really good Y alignment. All right, now we've grown this thin oxide here, and that's the brown regions. And this shows individual transistors of various lengths and widths. And this shows this oscillator circuit coming together very nicely. The next step is to pattern regions for contact cut openings that allow us to get down to those regions that we implanted and wire these transistors together. This is the third level, so we have 2 to the third or 8 possible cross sections, and you can see we're using 1, 2, 3, 4, 5 of the 8 now. And we have very good alignment, and this is down to those brownish openings, where we're going to again etch with hydrofluoric acid. This shows the result after we stripped off the photoresist, and we have bare silicon here, which aluminum can make contact to for wiring. And we see these contact openings in the circuit that we have over here. And now we're on to the fourth step. We have deposited aluminum by evaporation. Basically, we take a pellet of aluminum and put it in a basket inside of a vacuum chamber. We pass a current through this conductive basket, which in turn melts the aluminum, and it coats the whole inside of the chamber, including our wafer. But what that means is everything is short-circuited by that aluminum layer. So we have to apply the photoresist and do our fourth patterning to etch away the aluminum everywhere but where we want pads to electrically probe the devices or wires to connect things. So this is the photoresist over the blanket of aluminum before the aluminum etch, and the blue areas are these aluminum pads and wires. Now we're going to do the aluminum etch. This is a dry etch with gases, And this actually uses chlorine to etch the aluminum here. And this is a picture of that same transistor with the aluminum removed over this greenish oxide and the photoresist removed over top of the protected aluminum. So this is the aluminum gate electrode that controls the on-off of the switch. This is aluminum wiring to this contact, and this is the aluminum wiring to that contact. So we've made one transistor in this particular example, but now we're going to go and look at that whoops, wait a minute. I forgot the next slide. This is that finished electric field effect transistor, and we can, by the patterns that we designed in the computer, we can control the width, which directly influences the amount of current that can flow, and we can control the length of the transistor. Now, the trend is that we always want to make this smaller and smaller, so we might have to look at different processes. Do we want to use something other than silicon? Do we want to do something other than glass? Do we want to use copper instead of aluminum? How do we shrink this? So it's the materials and processes that we need to use our critical thinking if we were to improve on this. And this is a top-down and cross-sectional view of the transistor. The cross-sectional view is if we were to cut it horizontally and look at it edge on. So this would be the silicon. This right here would be the source. This over here would be the drain. The gate region is this very thin dielectric in the middle, and the pink down below is the aluminum, and those are the contacts that you see here and here. And then this is that more complicated circuit. This has got something like 20 or 25 transistors in it. So it doesn't have 100, it doesn't have 1,000, it doesn't have 1,000,000 or 1,000,000,000, but it puts us on the path to understanding that. And you can see one level of aluminum wiring. In modern integrated circuits, they have 12, 15, 20 different levels of wiring, not to mention all of the stuff that goes into making these circuits. This is a much more complicated CMOS ring oscillator here. This design takes 13 mask levels, where this technology takes 4 mask levels. Modern CMOS is up to like 40 or more masking levels. So to understand this, you have to first, I think, go through this, which is what I just did. Now, what about a 40 mask CMOS process? 2 binary choices for each of 40 layers is 2 to the 40th or 10 to the 12th combination of layers. Now, not all of those layers are useful. Some are, some aren't. How do you check for all of those? They all have to be aligned. Wow, there's lots of combinations. What if I have a process, this PMOS process has about 30 steps. What if I had a process that had 1,000 steps? And what if I was making the circuit not with 25 transistors connected, but 100 billion transistors connected? You need computers, artificial intelligence to help and check and everything. So there's a lot, again, that goes into all of this. So we've gotten to the point where we've completed a wafer with 300 identical copies of the original chip design. Now, not all of these copies are going to work. Out at the edges, sometimes there's more defects and so on. A particle does fall on here once in a while, or we have some other issues. So we talk about the yield out of 300, right? You know, we could talk about what would be 90% yield, what would be 80% yield. We're always striving to get that yield as close to 100% as we can. But it could be costly to increase that yield. But we build that into the sale price of the chips that we're making. And so now we have to test these devices to see which ones work or don't work. That's where we get the yield percentage. So we can look at parameters of the transistors first and decide whether or not we have a chance. And then we can look at the functionality of the circuitry, for example. So this is an example of parametric testing with statistics. We're looking for yield and also uniformity. Is it the same on this transistor as the neighboring transistor? And is it the same on the next chip as on this chip, or on the left side of the wafer compared to the right side of the wafer? This is showing a little bit different design of a single transistor here with the source and drain and a gate. These numbers refer to pins that we have that are sending signals in and out of this from test equipment. And we then look at the results and say, how are the parameters for this? So this is a wafer parametric map where whatever number that we're looking at, here's some numbers, 41, 45, 50, and so on. And we can put some ranges in here and color code it, maybe with red being bad and the blue being good or the green being good. And we can look at the distribution and say, oh, something's happening on this side of the wafer. And when did this happen? Did it happen on step 5? Let's go see if we can fix that or not. So this is done, you know, we do it in an Excel spreadsheet, but there's all kinds of software to help doing this. And once we've mapped these parameters, we say, hey, we got a pretty good chance of things working. We could go to that ring oscillator, which has got all those transistors connected together. And it will either pass or fail. It'll either oscillate or it doesn't work. So here's 3 examples of it oscillating. And this is at a supply voltage of -6 volts, and it's at a kilohertz range. I should say this technology I'm talking about is very slow. Here's a -10 volt range. When I crank up the power supply, it gets faster, megahertz instead of kilohertz. And if I go to -15 volts, it gets even faster. So I'd have to go to every single ring oscillator and say, yep, they all work. That would be 100% yield. Or, uh-oh, only 50% of them work. Let's find out why. And over what power range do they work? Maybe some of them work at -15, but some of them fail at -12. That's also something to test and understand. So the story I want you to tell at the end of this presentation is that microelectronics is very important. I want you to go and tell that to anybody that you know in high school that's considering a career. And then it combines science and engineering, but you can make it have an impact on anything you want to do. If you want to do entertainment, they need chips for doing fancy light shows and computer animation and so on, or put a chip in a soccer ball to see when it crosses the goal line. And you and this high school student can understand this stuff if you start at the beginning, take simple steps and explain them like I did, and then use your critical thinking as you go through courses and say, how can I apply this to the new devices through better materials and processing? And really the sky's the limit for what the microelectronics and semiconductor industry is going to achieve in the future through all these young people when I'm retired. And I think I have one more slide that was what Baljit wanted me to cover. And so I won't go to that, and this will be the end of the presentation. Thank you.
Excellent. This was just amazing. Let's go back. I'm going to take over. Rob, are you able to see my screen?
Yes, I can.
Okay. All right. Amazing. I truly believe that each of the slide could be a 40-minute lecture by itself. But the way you explained, Rob, right at a basic level and covering all the key elements of manufacturing is going to be very helpful for our listeners. I'm going to cover the next part of it. Semiconductor has a huge potential. We are surrounded by semiconductor chips all around, be it television, refrigerator, microwave, even entertainment. Rob mentioned the LED lights. It's all about semiconductor. Data 2021, 1.14 trillion chips were sold worldwide, which equates to 140 chips for every person on this planet. So it's amazing the number of chips that we are consuming, be it our car, be it even bicycles now with the motorized bicycles that are coming. Everything that we see around has semiconductor chips. When you have so many, when the demand is so high, the skilled career options are also very high. It is being predicted by 2030, industry is going to require approximately 1 million skilled workers. That means translating to 100,000 every new hires each year. India, Rob, just to let you know, is seeing a major investment boom right now. Every large company, be it Micron, just signed an agreement a week ago. Every large company is looking to kind of build semiconductor plants in India now. So this essentially kind of means a lot of jobs that are coming up in semiconductor field. The typical jobs that are there in the semiconductor field are semiconductor engineer. You can become an equipment engineer, you can become a process engineer in a manufacturing fab, manufacturing yield engineer. Field application engineers are more towards the equipment manufacturers, the equipments that Rob showed in the pictures, the large equipments. So the companies like Applied Materials, Lam, they hire field application engineers that go and service companies, the manufacturers like Intel's and Motorola's world. So you have jobs like field application engineers, customer service engineer. Further on in the fab, again, coming back, process integration engineers, photolithography, device engineers, operators. So be it when a fab comes, it creates a complete ecosystem around it. It is not about people working in it, but a complete ecosystem that comes with the manufacturing plant. Average salaries, we kind of looked at it. A field application engineer gets about 97,000 US dollars per year. That's the average, national average in US right now. What are we doing for India in semiconductor? So we have started a 1-year postgraduate diploma with advanced learning and a 6-month paid internship. So I'll go deeper into each what we are offering. First of all, I'm privileged not only being a student from RIT, we are partnering with RIT, Rochester Institute of Technology, for the advanced learning program of our postgraduate diploma in semiconductor and cybersecurity. We have partnered with RIT. RIT is located very close, about an hour from Niagara Falls. It's in the state of New York. I wanted to kind of show a quick video, a glimpse of
the first school that offered this type of program in microelectronic engineering, and it's an excellent program. I'm Lisa Minwell. I graduated in 1987 from microelectronic engineering. We were able to take what we were learning in the classroom and apply it in the lab. You got not just the theory, but also the application. We learned all the different aspects to semiconductors in our particular field. And to be able to participate in technology and technology development like that, it is very, very exciting. And not many schools have it. I started in research and development at Motorola, and the people I was working with were PhDs. And I had absolutely no problem working alongside of them and making contributions. So I felt very prepared. The people, the staff that work here are just incredible. Being a female and starting in the 80s in this particular program was a little bit daunting. There weren't very many female engineers, but the staff here always made me feel like I was on par with everyone else. This was
So that's a short video about the RIT program. It's an amazing, I'm a graduate of that. So just coming what we are offering. So it's a postgraduate diploma. In India, we have partnered for this diploma with Rahat Bahara University. It's a university in Mohali, Punjab. What we are offering is a 1-year program and then a 6 months paid internship. The eligibility of this program is a 4-year engineering degree. The participants can be of any field, be it electrical, electronic, computer science. So I'm going to go through what exactly the program is. 9 months out of that 1 year, student is going to spend learning not only technical, but also soft skills in India. This is going to be at Rahat Bara University. Post that, they will have 3 options for advanced learning. They can do the advanced learning in India. They can do an advanced learning in US or Israel. And like I mentioned, 9 months is foundation building. In foundation building, we are focusing both on technical and soft skills. And then hands-on experience on advanced labs. Internship, which is after 1 year, it's going to be a paid internship. It's optional. Ajuba will line up 3 interviews for each participants. So we will focus only on lining up the interviews. Then it essentially is between the student and the corporate who is hiring you. So that's why we have made the internship optional. I'm going to go over even the fee structure with people that are hearing. Like I mentioned, what we have done is we have given options to the students. The first 9 months in India, the fee is 2 lakh rupees. So the fee for 9 months is 2 lakhs. I'm going to cover the advanced learning options, all 3 options with you. Number 1 option is you can opt for India itself. If we are doing in India, we do not have semiconductor lab. It will be focused on design level internship. So design level internship, if you opt for India, here the advanced training fee is 1.5 lakhs and 1 week in Bangalore with our partner corporate, where you will see how the design are being made. That is 0.5 lakhs. It covers your travel, lodging, and boarding. So a total fee of 4 lakhs if you opt for India for your advanced learning. Now, if you opt for USA at RIT for your advanced learning, the fee for India remains the same, but there is an additional fee of 1.5 lakhs, which is for overseas coordination and management fee. The 3 months in US, it covers advanced training, which is 15 lakhs. And then the other 2 options are a 10-week, your complete housing, food, a twin sharing option is 2.21 lakhs, and travel and visa is 3.5 lakhs. Now, travel and visa, for example, it's optional. You can say that, hey, I will manage my own visa. I will manage my own travel. You can do it by yourself. We are giving that option to students. Now, third option is Israel. So fee for 9 months remains the same, 2 lakhs. Same fee for overseas coordination and management fee, which is 1.5 lakhs. The 3 months in Israel, advanced training is 9.5 lakhs. Housing and food on twin sharing is 1.23 lakhs. Now, travel and visa fee, again, we made it optional, 3.5 lakhs, which is the same. So what we have tried to do is we have tried to create options for the students. They can pick for advanced learning either in India, USA, or Israel based upon what fee capabilities that they can pay. Finally is after 1 year, you will essentially get an option to do an internship. Just to give you some numbers, like I had mentioned earlier, national average per year is $97,425 US per year, which equates to 8,119. In Indian rupees, it's 6.6 lakhs approximately per month. An average internship at a lower number, a student will make about 3,500 per month. This is a lower number. It could also go up to 5,000. So 3,500 per month is about 2.87 lakhs Indian rupees per month. So in an average, you will make about 17 lakhs in 6 months. So essentially, if you look at it, you can cover your 1 year postgraduate with the internship. In fact, I'm proud to say I learned about this at RIT, because RIT offers co-op. Internship is also a co-op being called at RIT. So while you are from your third year onwards in a 4 or 5 year degree, you do 6 months at school and 6 months in the industry, and you make money to pay your tuition. So we kind of integrated those learning into this program, where you spend 1 year learning, 9 months in India, and 3 months we have given options, and 6 months with the internship, you will essentially make what you have spent. Admissions are open. Let's kind of join. I kind of would request everybody that's listening to propel this to all your known friends, family members, because this is semiconductor is an amazing field. It's new to India, so we are trying to educate everybody on the potential and what is available out there. So you can take a picture of this slide, the QR scan, you can go directly on our website and register it. It's an amazing collaboration that's happening to bring this to India. So this postgraduate diploma, which is being offered at Rahat Bahara, you will get a degree from postgraduate diploma degree from Rahat Bahara on this. 9 months at Rahat Bahara, and with advanced learning options, whether you want to do it in India, US, or Israel. Rob, I want to kind of switch to our Q&A session now. When registrations were happening, there were a lot of questions that were part of registration that was done. So I'm going to kind of take one at a time. We will hear from you. So first one, I will bucket it together in advanced semiconductor technology. The question is, could you kind of give us a brief about the emerging trends and advancements in semiconductor technology, introduction to advanced materials specifically? I see that you covered 3 and 5 compound, but how about 2D materials?
I wanted to pull up, I'm just trying to pull up my actual written responses there so I can recall what I had said to you, Buzzy. Yeah, so like I said to you, I think, the emerging trends and advancement is really the new materials like silicon carbide and gallium nitride are really increasing in importance, especially when we look at high power applications like electric vehicles or electric bikes and so on, that have operating voltages in the 400 to 800 volt range. So an example is Wolfspeed has just opened a brand new 200 millimeter fab in the United States for production of silicon carbide power devices. And there's a lot of people that are looking at gallium nitride power devices as well. But the silicon carbide, for example, requires ion implantation of aluminum and special high temperature wafer chucks to hold it. It takes super high temperature, like 1700 degrees centigrade anneals. So there's all these specialized processes that go into some of these things. As far as 2D materials, working with things like graphene or moly disulfide, a lot of times the transfer or growth of these monolayers or bilayers of materials are very difficult, and it's very difficult also to kind of make the devices exactly where you want them so that they can be efficiently hooked up with a high yield like we currently see in regular silicon processing. So does that answer your question,
Yeah. Thanks, Rob. The next one is, can you talk a little bit about the advancements in semiconductor packaging, especially how packaging contributes to improved performance and miniature of semiconductor devices.
Yeah, so for many years, the improvements in semiconductor systems was simply achieved by making the devices smaller and putting more devices together. But what we've seen now is more specialized parts to the circuit, like cache memory has to be close to the processor, and multi-core memory, and so on. So we're getting back to having chiplets that might be of different materials and different processes, all optimized to do what they do best, but having to be integrated into the larger system. So you need to have a bank of these pre-tested chiplets that you know that they work, and then you have to figure out how to connect them. And it's not done by going down to a printed circuit board with very large features. You do something called an interposer, which has got dimensions that are almost of the same size as the chip itself, so that you can get a very dense packaging of highly optimized components, subcomponents. So that's really the trend, I think, in packaging and interconnecting at the system level. So it's not so much the performance of the transistors that are driving the improvements now, it's the holistic improvement of the entire system, packaging, interconnects, and so forth that are driving the improvements.
Excellent, thanks, Rob. Next one is around the semiconductor failure analysis. Could you talk about the key failure analysis technologies for root cause failure investigation?
Well, first off, I'm going to admit that I'm not really an expert on failure analysis, but I can give you my thoughts there. Failure analysis is really tied to data collection and, what you can get out of the lab and out of the individual tools and how you record it and work with it. So this starts with doing defect inspections and particle counts and maps during the manufacturing process, and then adjusting your protocols to reduce defects and reduce particle counts and improve your clean room. But this has to be tied to any yield improvement efforts so that you make a higher yield, which makes you more money in the long run. And then when you're all done with the processing, you need to have test data collection and maps that are either done at the wafer probe level or perhaps in line to tie to the defect maps. And then you correlate the defect maps and the particle maps to the test maps, like I showed in my presentation, and say, what's going on over here on this side of the wafer? Was it that side of the wafer was up in a particular tool, or this side was down and the acid wasn't the same strength there? What can we do to improve that, and so forth? So fabs use what's called failure mode effects analysis to investigate and prioritize the failure modes so that they can work on reducing them. And it turns out that artificial intelligence has really proven to be very useful in uncovering all of these very subtle, nuanced failure effects.
Excellent. Thanks, Rob. Let's go to the next one. The next bucket of questions came around environment, clean room practices. So the question is the importance of clean room practices in semiconductor manufacturing, safety protocols, especially when you're looking at the clean room environment.
Well, as a teacher, I really value the importance of conveying these clean room protocols and practices to the students. All right. I don't care if you have a room that's painted white that's not a clean room. If you go into that clean room and you pretend to follow all the protocols, you will be learning how to go into the real clean room, and you never get another chance to do it right the first time. That's a saying that I really like. And so some people feel that maybe some of these personal protocols and clean rooms have become less important because there's more automation in the industry and closed wafer carriers and automated monorail systems moving the wafers around, and the tools have built-in wafer handling, so you don't pick things up with tweezers anymore, and so on. But I really think that students need to understand the protocols. It might be transferring to how do you work on the equipment, more than how do you touch the wafers or work with the wafers. And then as far as safety goes, safety should be a combination of very well thought out standard operating procedures, but the student needs to have reasoned critical thinking about what the risks are that they face and the costs of following these procedures and implementing them. Sometimes people say, well, skipping these processes could, save us some money. But in the long run, not doing good protocols for contamination control and safety, I think eventually lead to lower yields and higher risks.
Excellent. Next one is around environment. What are the environment challenges associated with semiconductor manufacturing?
Well, I think the environmental challenges are primarily due to the scale of how much materials and chemicals are used, gases and chemicals that also have to be treated as they leave the facilities. So the amount of water used is absolutely incredible. So we see wafer fabs being located in the United States, like near the Great Lakes, which are some of the largest freshwater supplies in the world. So drying, rinsing the wafers and scrubbing the gases and cleaning that water up again is very important. And having dry wafer cleaning that doesn't use as much water is something that a lot of people in the industry are very interested in. They're also looking at recycling water, the gray water, after it's been treated. Maybe you could use it for cooling where it doesn't actually touch the product and the contamination issues are smaller. SEMI, which is a worldwide semiconductor equipment organization, has many green manufacturing initiatives that people could research and get involved in.
Excellent, thank you. Next one, Rob, is the future of semiconductor manufacturing. Essentially, we both have seen how the industry has kind of moved from 100 millimeter to 300 and beyond now. So could you talk a little bit about where the future of manufacturing is moving?
Well, we didn't really move beyond 300. There was a lot of talk about 450, and that has pretty much died out for the main reason that the expense of developing the tools and buying the tools and implementing a full 450 millimeter fab was astronomical. And there was probably only going to be 3 companies in the world that were ever going to be able to afford to do it, and they balked at doing that. Now, that doesn't mean that the whole world is 300 millimeter. There's plenty of opportunities for 250 and 150 millimeter wafer processing fabs to do maybe smaller volume, boutique, more focused, unusual type of processing. So for that reason, it's been very hard for us at universities to get used 200 or 150 millimeter wafer processing tools, because there's companies out there that are using those tools to still make a very good profit doing chips that are maybe not quite leading edge, but still very much in demand.
Excellent, thanks. The next one is on the career opportunities in semiconductor. Maybe I can take this one, Rob. What are the potential career paths and opportunities in semiconductor industry? I'll make it relevant to India. So, when an industry like semiconductor comes to India, there are 2 types of...
David?
Yeah, Rob?
Quick one for you. Since I'm in a hotel, I have to check out in a few minutes. I was wondering if maybe we could open it up to any questions that people might have directly for me. And if there are some, I can tackle them. And if there aren't any, I can let you finish up and I could go check out.
Yeah. No issues, Rob. I think the whole session was so interesting that we took more than 1 hour.
Yep.
I will cover the last question. You can go ahead and check out. I really want to appreciate your time. It was just an amazing session, how you covered all the basics of it and all the Q&A session. Thanks again, Rob. I look forward to being in touch with you.
All right, I will sign off now then. Thank you.
Thank you. So the next
bye-bye.
question, thank you. Next question was on the career opportunities in semiconductor. So when you're looking at semiconductor, there are two types of companies that are coming into India, for example. One is the chip manufacturers or the semiconductor manufacturers like Intel, Motorola, Micron, Texas Instruments. They are going to be coming to India. The second is on the equipment manufacturers, the companies that are providing equipment or services around the chip manufacturing companies, like Applied Materials, Novellus, Lam, and so on and so on. So if you look at the job opportunities out there in the semiconductor, as well as fab, as well as equipment manufacturing, engineers are required. So the postgraduate diploma will enable you to get jobs both sides, at the chip manufacturing plant as well as equipment manufacturing. Now, within the equipment manufacturing, there is quite versatile job offerings. For example, I mentioned about field application engineers or customer support engineers. In fact, these are two interesting job opportunities because you get to travel quite a bit all across the globe. I trained quite a few application engineers at Applied Materials, for example. They traveled all across from Taiwan, US, Japan, Korea, wherever the applied equipments are installed. As a field application engineer, you go and teach your customers how to use that. So all these, if you are at an engineer level, so that what we are offering, the precursor, the prerequisite requirement is you need to have an engineering degree. Once you have all the bases, be it electrical, electronics, computers, or any engineering degree, you can enroll in our program, which is for 1 year, and then internship. Then all the career options are open for you, be it in a working in a fab or be it with the equipment manufacturers. The companies that you will be doing internship, you could probably end up with a job globally. A person that I trained in Bangalore, he is currently with Samsung in Korea. So it's amazing how people get opportunities in life. So that was the last question. We will move on to our next slide, which is essentially our next webinar. So we're going to switch from semiconductor to cybersecurity for our next webinar. We got a lot of inputs that we should move the webinar to Sunday. So moving forward, we will be hosting our webinars on Sunday. So next webinar is going to be on Sunday, July 16th at 8 p.m. India time. We will cover ransomware. We'll look at current trends, data recovery, and prevention strategies. So I would urge everybody who's listening to register. You can essentially take a picture of this slide, do a QR scan, and you will go directly on our website where you will get further details of what are going to be covered in this session. I hope to see you all Sunday, July 16th at 8 p.m. India time, which is 10:30 New York time. Again, thank you all for your active participation, and we look forward to skilling India with our free webinars that we are providing. Thank you.